Good afternoon. So we approach the final of this course. We have 4 more lessons to learn yet another topic, another unit of this class, namely the parametric equations. So curves defined by parametric equations and some calculus related topics and how to handle them using parametric equations. Not an overly complicated topic, but a very important one because parametric equations appear quite often in many other courses many of you will have to take after this class. In particular, Calculus 3. You'll make use of these. As an example, polar equations, polar coordinates, curves given in polar coordinates are basically an example of parametric equations, and it is known that many problems are much better suited in polar coordinates than Cartesian coordinates. So you could see that not just in Calculus 3, but in other courses like partial differential equations and many other subjects later. So if it's completely new to you, give it some time to understand the main idea behind the concept. So today we're just gonna basically introduce the main, the overall definition of a parametric equation or a parametric curve, and illustrate with some examples on how to sketch them and maybe how to change a problem from parametric equation to Cartesian formats and vice versa maybe. So let me introduce the concept by looking at an example that illustrates the motion of a particle in the plane, right, in the Cartesian plane. So if it's a motion, then that means you could tell the position of the particle at various time points. So let's say you look at the clock as the particle moves along a path, and you register the position of the particle at various time points. So I'm not going to specify the actual function at this point. Just really imagine a motion, like the path of that motion. Can go like that, for example. So with the arrows, I'm indicating basically the direction of motion. And right off the bat, notice that this path, although I give it in the coordinate system, in the traditional coordinate system with the x and the y axis, doesn't really represent a function in the traditional sense as you're used to. It doesn't satisfy the vertical line test, if you remember, right? So for this to be a function of x, for example, it cannot be such a thing because any vertical line will, a vertical line can intersect the graph in 2 points. So for it to be a function, in fact, let's just write it down. This can't be the graph of some function y equals h of x, let's say. Because to be a function, remember, for every x, you need to have one, at most one y coordinate. In other words, if x is in the domain, you need to have a unique y coordinate, not 2, as you could see here if you look at the so-called vertical line test. So I'm mentioning this because right off the bat, parametric equations give you more flexibility in the sense that they can represent functions, but they can also extend to any other forms. In this case, in the plane, just really any path. Doesn't have to be the graph of a function in the traditional sense. Now back to what I said, let's suppose that you look at the motion of this particle and you say, okay, well, when you started to look at the chronometer, let's say the particle was here, or I make the dot line here. So let's say at this point, the time t equals 0 when the particle was at that point. And then later in the path, let's say when the particle reaches this point here, the time value is t equals 2 minutes later. So let's say the time is denoted in t and it's measured in minutes. And then maybe over here the time t equals 5, and maybe when it's here the time t equals 20, and maybe when it's here the time t equals 30, when it's basically kind of back to close to the point where you started from, but you know, after you went through this path. So the point to be made is, obviously if you pick any point on the path, any point of coordinates x, y, clearly you can view each x and y, each coordinate x and y, as functions of the time t. So in other words, this path can be described by two functions of t, which is called a parameter. So this third variable, right? So you have the curve identified obviously by the x and the y coordinates, because after all it's a curve in the plane. But in turn, each of these coordinates x and y is a function of t. So let's write it as a definition. Suppose x and y are functions of t. Like I said, this is called a parameter. It doesn't have to be denoted by t. Most of the time you'll see t because there's this analogy with the time. But for example, in the case of polar coordinates, we use theta because that's a traditional notation for the angle, which is the polar angle, which is the parameter in this case. Then these two functions form the so-called parametric curve, which again is described by specifying for each coordinate the functions of t, right? So each coordinate is a function of t. Obviously, you're going to have also a parameter domain, which can be all real numbers, or it could be just an interval, right? Because you can have a path that you measure it from a time value to another time value, not just for the whole real axis. It can be, but it doesn't have to be. So obviously, if you were to sketch a parametric curve, you must plug in the initial and the end point of the domain, A and B, and maybe some points in between to have an idea on the shape of that path, if you can, of course, sketch it. If it's too complicated, then the computer could do that for you. We're going to go over, obviously, a couple of examples in the next page. So at this point, again, this is the main motivation. Lots of problems, especially, for instance, motion-related problems, are better described often by parametric equations. And moreover, you have far more generality with parametric equations. And you also have extra pieces of information. For example, you can tell the direction of motion on the curve. If I give you, as you'll see in an example later, if I give you the curve in terms of x and y without the time information, you won't know how the motion, the direction of motion, right? There are two possible directions of motion on any curve, right? One way or the opposite way along the path. So with parametric curves, you could tell the direction of motion because by plugging in t from A to B, you know where you go from which point to another along the curve, which is the reason you could put these arrows when you sketch that curve. So with that in mind, I think we're going to move on to the second page so we can start from a clean slide and tackle some examples. So stay tuned. All right, so for our first example, let's say we want to sketch the parametric curve given by x equals t minus 1, y equals t squared minus 3, with the parameter domain 0 and 3. So t between 0 and 3. So we want to sketch this. Now, most of the time we're going to use computers to sketch more complicated parametric curves. Basically, the surest way to do it by hand is to actually identify the curve by a known curve. So often we eliminate the parameter, as I'll show you immediately, and and then we recognize the shape of the curve, we sketch it, and then that's it. But in some other cases, especially if the functions that represent x and y are pretty much arbitrary, it's impossible to recognize the shape of the curve beforehand. Even if you eliminate the parameter, it's not easy to actually sketch it. So then we could basically sketch several points, the more the better, to give an overall idea on the shape of this curve. So at this point in this section, when the problem says to sketch, all you got to do is to plug in the endpoints of the domain and some points in between. And it's best in the beginning to do a table and make sure you don't confuse, of course, the parameter values with the actual values of the x and the y coordinate, because obviously what you plot in the to get the sketch of that curve are the values of x and y corresponding to these parameter values. So the parameter is from 0 to 3. I'm going to have to plug in 0 and 3 because that's the start and the final point of the curve. And then some points in between, let's say 1 and 2. But any point can do. So you have basically a sample of points in between the endpoints of the domain. So if t is 0, then x is minus 1, y is minus 3. If t is 1, 1 minus 1 is 0, 1 squared minus 3 is minus 2. If t equals 2, 2 minus 1 is 1. 2 squared minus 3 is 1. Right? So when t equals 1, just to make it clear, x is 1 minus 1, y equals 1 squared minus 3, which is minus 2, right? And same thing for the other points. And then when t equals 3, x is 3 minus 1, which is 2. And then 3 squared, that's 9 minus 3, that's 6. All right, so let's sketch this curve over here. And let's say, let's see if I have enough room here. So suppose x minus 1 is over here, minus 1, and then minus 3 will be here. So that's the first point. And then x equals 0, y equals minus 2 will be this point. That's minus 2, that's minus 3, minus 1. Then 1, 1. Over here, and then 2, 6. 2, 1, 2, 3, 4, 5, 6. This is actually a portion of a parabola. And so notice this is the direction of motion, right? Because this is the initial point, which corresponds to t equals 0. And this is the final point of that motion, which corresponds to t equals 3. And then you have the other points in between. Now, it's not too hard. Well, it might be hard in the beginning, but with a little bit of practice, it's not going to be hard to recognize that this path is basically a portion of a parabola. Because in this case, actually, you can recognize or you can compute the parabola in terms of x and y where this curve comes from. And I'll show you that immediately. But this is how you sketch it. Some problems in the homework or later on in life, you may have to basically figure out the curve in terms of x and y. So basically you want to eliminate the parameter t. Often we do this just to recognize the curve if it's possible, although the whole point, if you ask me, in this chapter is to learn how to actually do calculus with parametric curves without reverting back to the Cartesian coordinates, I mean to the curve in terms of x and y. We do that again if it's possible and we just to recognize the curve, but often the whole point is basically to work with parametric equations from the beginning to the end, precisely because in more complicated examples, it's not easy to eliminate the parameter. But in this case, we can do it. The way to eliminate the parameter, there's no specific way. I mean, it just depends on the expressions you have. Roughly speaking, you want to solve for t in one of the equations and plug it in the other one. So you decide which one to pick. Obviously, you can pick the easier one. So if I look at the parametric curves x equals t minus 1, y equals t squared minus 3, I can choose the first one and I get t equals x plus 1 and y equals x plus 1 squared. So you plug it in into the second equation and that gives you, you can leave it like that, or you can expand it, x squared plus 2x plus 1 minus 3, which is x squared plus 2x minus 2. So this is actually a parabola whose vertex is, what is it? Minus 1 and minus 3. So actually this is the vertex here. So if you were to actually sketch the parabola, so if someone says, okay, well, the motion occurs on this parabola, of course you could sketch the full parabola like that. But obviously the motion, because t is restricted between 0 and 3, and that corresponds to x being restricted between minus 1 and 2, if you look at the table above, that means the motion is just on a piece of the parabola. So the parabola, the motion is restricted to just that segment that is emphasized on the left picture here. But notice that if you eliminate t, you lose the information about the direction of motion. So that is the value of the parametric curves, right? I mean, if someone says you have a particle that moves on this parabola, that doesn't tell you the direction of motion. Does it go from bottom up or from top to down? And that's why with parametric curves you always have more information about what goes on in this motion. So speaking about moving from parametric equations to Cartesian coordinates, there is another class of functions coming from polar coordinates, which we'll talk about in more details later, in which the way to remove the parameter is to use trigonometric functions. So for example, let's say you have the following parametric equation: x equals 4 sine of theta, y equals 4 cosine of theta, with theta being the parameter. Now let's say theta is between 0 and 2 pi, right? So that's the parameter domain. So when you have things like that, and the question is to eliminate theta, use the fact that sine squared theta plus cosine squared theta is equal to 1. That's the easiest way to eliminate the parameter. Rather than, of course, making the substitution like before, right? So you get theta, sine, and cosine by itself in terms of x and y, and use this formula to essentially eliminate theta. So for example, in this case, from the first equation, sine of theta is x over 4, cosine of theta is y over 4. And using the formula, sine squared theta plus cosine squared theta is x over 4 squared plus y over 4 squared, which is equal to 1, because again, from the trigonometric formula, this is also equal to 1. So obviously this is a circle. I mean, I hope you guys notice that if I simplify this expression here, this is x squared plus y squared over 16. And if I multiply by 16, I get x squared plus y squared equals 16, which is the equation of a circle of radius 4. So we're going to do more examples obviously on the next page, but I want to emphasize that circles or round objects in general are very suitable for this type of parameter. Again, these are essentially polar coordinates. Like I said, we'll talk about this in more details in a couple of lectures. And the fact it's a full circle because theta is, by the way, between 0 and 2 pi. So that goes all the way around the unit circle here. I mean, the circle of radius 4 in this case, but 0 to pi means the full circle. Polar coordinates often are much easier to deal with in calculus. For example, if I want to get y as a function of x, then that's plus minus square root of 16 minus x squared, and we know that things like that are hard to deal with in calculus, to integrate or do more other things like that. And often if instead we work with parametric equations, that's just much easier. And in polar coordinates is as easy as it gets actually in terms of representing a circle. So let me continue now with another example similar to problem 1, a slightly more complicated one. And then after that, we'll see maybe another example and we'll call it a day. So stay tuned for the next page. All right, so another one, which actually is kind of hard, if not impossible, to eliminate the parameter, right? So it's x equals t plus sine of t, y equals cosine of t. And t is between minus pi and pi. So let's just sketch this one as well with the table of values. So let's say t is over here, x and y. Obviously, we have to plug in minus pi and pi. And for the points in between, let's say I plug in minus pi over 2, 0, and pi over 2. Again, there's no rule on which points you should plug in. It just basically has to be a represented sample. So when I plug in minus pi, so let's see, if t equals minus pi, I get x equals minus pi plus sine of minus pi. Sine of minus pi is 0, so that ends up being minus pi. Cosine of minus pi is like cosine of pi, which is minus 1. So that's minus pi and minus 1. When t equals minus pi over 2, we have x equals minus pi over 2 plus sine of minus pi over 2. Feel free to use the calculator for some of these if you find it more comfortable. This is minus pi over 2, and sine of minus pi over 2 is just minus 1. So minus pi over 2 minus 1. T plus sine over 2. Yeah, minus pi over 2 minus 1. For x, and this will be 0. I want to double check something. So, yeah. All right, so for 0, we can do this mentally. So 0 plus sine of 0, that's 0. Cosine of 0 is 1. And then when I plug in pi over 2, that's pi over 2 plus sine of pi over 2, which is pi over 2 plus 1. And then cosine of pi over 2 is 0. And finally, if I plug in pi, that's pi plus sine of pi, which is 0. So that's just pi. And cosine of pi is minus 1. So if you look at these values, these are the y coordinates. Let's see, the x coordinates are basically symmetric with respect to the y-axis. And the y coordinates as well. I mean, they basically go from minus 1 to 1 and then back to minus 1. So kind of looks like a semicircle. It's not a semicircle, but it kind of looks like one. So let's see if we can do a little sketch here. And minus pi minus, well, let's actually figure out where we place minus pi and pi, because the other ones are kind of symmetric, right? So let's see, minus pi over 2 minus 1, it's like minus 2 point something, so it's over here. And so in fact at this point the y coordinate is 0, so let's say this is minus pi over 2 minus 1, and this is pi over 2 plus 1. And then the actual y coordinate is minus 1 when x is minus pi and pi. So this is the initial point, this will be the final point over here. And the one in the middle is at coordinates 0 and 1. So this is equal to 1 here. All right, more or less. Direction of motion, of course, is from left to right, right? Because this is the initial point and this is the final point. So I think what I'm gonna do, and I don't know if, I don't think I'm gonna do actually a different page. I just want to finish with an example in which actually the domain, the parameter domain is minus infinity, infinity, because it doesn't have to be a closed interval. And in that case, you just take a sample of points to the best of your ability. Or if you can, if you can recognize the curve, if you can eliminate the parameter quickly, you should do that just to have an idea how the curve looks like, because it might be easier to sketch in that situation. So here's a quick example. Let's say x is equal to e to the t and y equals e to the 2t. This, and I'm not going to say anything about any restrictions for t. So t can be any real number, all right, minus infinity, infinity. And in this case, t can be eliminated pretty easily if you look carefully. Because notice y is e to the t quantity to the power 2. So it's not overly difficult to recognize that the curve is basically a parabola, right? So I mean, if x is e to the t, I can plug it in into the second curve. So that's just a parabola. And it's the whole parabola because t, well, hold on a second. Actually, not the whole parabola because e to the minus infinity goes to 0, right? So let's get to that part immediately. But the whole point is that the curve, the parametric curve, sits on a parabola y equals x squared. Use a dotted line like that. And then let's see what portion of it is actually given by this parametric curve. Well, in terms of the sample of values, notice if I do the table like before, let's start with, for example, with 0, which is going to be in the middle, right? If I plug in 0, t equals 0, then x is going to be e to the 0, which is 1, and y e to the 0 again, which is 1. So that's going to be a point on the curve. But as you plug in negative values, x and y are still positive. So remember, let's write here on the top of the page. As t approaches minus infinity or goes to minus infinity, e to the minus infinity is 0 in the limit sense, right? Same thing for e to the 2t, right? I mean, that's also something that goes to 0. So actually, this curve is giving you the right half of the parabola, right? So as t approaches in minus infinity, both x and y approach 0. It's not going to touch actually 0, 0. It's in the limit sense. And then as t goes to infinity, you have all the other points, right? So for example, if t equals minus 1, you have e to the minus 1, which is 1 over e, and e to the minus 2, which is 1 over e squared. So all of these points will cluster closer and closer to 0. So if you were to sketch the entire motion, it starts near 0, 0, near the origin, and goes to infinity to the right hand side, and that's the direction of motion. As you move on the parameter domain from minus infinity to infinity, you trace the right half of the parabola starting very close to 0, 0, and then all the way up to infinity. And in fact, the speed of motion will increase, obviously, right? So for example, if you go with t equals 2, x will be e squared e to the fourth and y e to the fourth, and then it's going to be faster and faster. I mean, you're going to go higher and higher faster with these coordinates, right? So e third and e to the sixth and so on. Okay, so I think that's enough for today. The next section will be also important because we're going to deal with some calculus tools related to parametric curves. So that's it for today.